Okay, number 45 is another problem where they're asking us four things here, guys, in no particular order, in the order we're going to find them in. We're going to look for a local max and min, actually critical points, then find any local max or min that we might have, then intervals of concavity and points of inflection. So let's get started. We're going to take our first derivative here, f prime. And by the way, just in case this is bothering you here at all, that's just really a statement on their part that's kind of reminding you that this function has a limited domain. Because of the x to the 1/2, which of course is a square root of x, we can't put in any negative numbers here and get a real result out. But luckily, they wrote this in the form that's probably easiest for us to differentiate. So here you go. F prime of x is going to give you a 2x, and then we're going to have a minus, I'm thinking ahead here, 4x to the negative 1/2, which I'm going to make 4, and then instead of x to the negative 1/2, we'll make that a square root of x down there on the bottom. Although as soon as I wrote that, you know what? That's going to be difficult to differentiate on the next step if I write it like that. So let me write it out the way it was, 4x to the negative 1/2, but now I'll go ahead and rewrite it the way I just did. I think this second version I'm working on right now will be easier to deal with, but the first version is easier to differentiate again on part 2 of this problem. Okay, guys, so there's our derivative. The only time this derivative would be undefined would be right here if that denominator were equal to 0. So basically, we know right now, and let's see, 0 is in the domain of this function, but it's really the left endpoint of this thing. This function begins at 0 and goes all the way towards positive infinity. So do we have to consider 0 a critical point? Kind of. So let's talk about how we're going to do that. 0 would make this thing undefined. So I am going to go ahead and list that as a potential critical point, but I also want to know what would make this whole thing equal 0, where 2x then would equal 4 over the square root of x. So if I multiplied both sides by the square root of x, I'd get an x to the 3/2 power over here on the left. And then if I divided by 2 on both sides, the 4 divided by 2 would get us a 2 there. And then I would get x by itself by taking both sides to the 2/3 power. That's not cool. All right, and those would cancel out, and we'd end up with x equals, and unfortunately, guys, there's nothing you can do here in number 45 to simplify that answer right there of 2 to the 2/3 power. It doesn't work because 2 is not a perfect cube. So I've got to write that as 2 to the 2/3. Not a whole lot of fun. So now I'm going to include x equals 0 because that is a value at which my derivative is undefined, and x equals 2 to the 2/3 power. And now something interesting happens, and this is the first time this year, as I'm recording this anyway, that this is going to occur. Normally, with 2 critical points, and by the way, there's my answer to the first part of that question, the critical points. Normally with 2, it would create 3 intervals. You draw a line here, this horizontal line across, and the first thing we would do now, guys, is right here, pick an x value less than 0, like for example, probably -1. But this statement right here serves to remind me that this function does not exist for any x values that are less than 0. So what that means, guys, let me get rid of that x equals -1 right there. This x equals 0 that we came up with right here is the hard left endpoint of this, and it does not exist. The function doesn't happen when x is less than 0. So I don't need to put in a number less than 0 because you can't. So in between them, I'd probably pick x equals 1, and then greater than 2 to the 2/3 power. Now you might be sitting here wondering, wait a minute, I don't know what 2 to the 2/3 is. You're probably right about that. But obviously, 2/3 as an exponent is smaller than 1. So 2 to the 1 is 2. 2 to the 2/3 then would have to be less than that. So I'm just going to pick, well, I was going to pick x equals 2, but if I was smart, I might think about putting a perfect square in there. How about something like x equals 4? Okay, and let's see what that does. So we're going to our first derivative now, guys, f prime of 1, and let's see where that's going to take us. I'm going to focus, I think, on this version of the first derivative right there, and let's see what happens when we put a 1 in there. The first term is going to become 2, and then minus 4 over 1, which is 4. 2 minus 4 is negative, and that means that f is decreasing on this interval of values between 0 and then 2 to the 2/3. But now, let's take our test value here of 4 and put that into the first derivative. 2 times 4 is going to be 8, and on the second term, the square root of 4 is 2, 4 over 2 is 2, and we end up with 8 minus 2. That's going to be positive, and f is going to increase then on that interval right there. Okay, so that's where we ended up with for our first derivative. So answering the first question, these are your critical points right here, but they also wanted to know where is this function, let me get my directions right here, guys, not increasing or decreasing. Do we have any local minima or local maxima? Well, again, you wouldn't really talk about this one right here, x equals 0, as being an absolute max or min, but right off the bat, this is where the function begins, and it immediately decreases. So we're starting, I'm just drawing a graph here somewhere, we're starting here, and the function goes down before eventually coming back up. That means that this point right here, x equals 0, is going to be a local maximum. So I'll go ahead and write that out. We've got a local maximum at x equals 0. And then what happens at our second critical point? Our behavior changes from decreasing to increasing, and that means that we have a local minimum, although if I'm not mistaken, I think that's actually an absolute minimum, but no need to overthink that. They just asked for local. A local minimum at x equals 2 to the 2/3 power. So that's kind of an ugly number, guys, but that's what it is. Okay, we are half done with this problem now, everybody. Now that we've got that, we need to move to our second derivative now and see what we can do. So I tell you what, I'm going to start, ooh, that was ugly. I'm going to start a whole new page right here. Oh, that's not copying with it there. Just a second here, everybody. What if I took all of that? Okay, and I think I can copy this, and I'll go to a new page. No, not that one. This one. Here we go. And I can paste that right here. And let me get rid of some of the junk that I didn't want there. Okay, so I thought back in the day here that stopping right there would probably be the best place as far as coming up with our second derivative. So let me move all that up and out of the way, and let's go now to find f double prime of x. Derivative of 2x is just going to be 2, and now we are going to have a plus, right? Negative times negative. The 1/2 times 4 is going to be a 2, and this would be x to the negative 3/2 power, or x to the positive 3/2 power down on the bottom of a fraction. Okay, so that's where we're at, all right? And we would want to think now about, all right, is there any value that's going to make this second derivative either 0 or undefined? And as far as being undefined goes right here, we can't let a denominator equal 0. So we are undefined at x equals 0. Got it. And as far as it equaling 0, I don't think that's going to happen. If we took 2 plus 2 over x to the 3/2 power and set it equal to 0, I'd probably bring this 2 to the other side to get started. 2 over x to the 3/2 would equal negative 2. Now I would do that trick when I switch these two things. So that would give me a 2 divided by negative 2, which is negative 1, and that would equal x to the 3/2 power. And at that point, trying to think of what this would look like right here, we would want to take both sides to the 2/3 power here, but I have a funny feeling this might not do what I want it to do, will it? See, when we square it, which is what we're doing here with the 2 in the exponent, we lose the sign here. We'd end up with an x over here on the right, but on the left, negative 1 to the 2/3 power, well, what that means, guys, is negative 1. It would be a cube root of all that, and then all of that would be squared. Now, this looks like it works. The cube root of negative 1 is negative 1, squared is positive 1. But as soon as I go back and look at what this looks like, if I were to put a positive 1 in right there, that would get us a positive 1 on the bottom. 2 divided by positive 1 is not equal to negative 2. So I don't think we have a solution to that equation right there. So I think the only potential point of inflection we have there is x equals 0. Okay, so that was a lot of work that didn't get us very far with that one, but I think that's where we're at. So I'm going to ignore all of this and just go with x equals 0 for the 1 value right here and make a sign chart from the second derivative from that. But I don't know what I just hit there. However, just like in the last problem, there's no point in picking anything less than 0 because it's outside the domain of this function. So let's pick x equals 1, nice and easy, and find out what's going on with our second derivative there. So I'm going to focus on this expression here for the second derivative, and if we were to plug a 1 in there, I think we can see pretty quickly that would end up being positive, and we are going to be concave up. So what's going on right here? They wanted intervals of concavity right here. So I think we can say that this graph of f is concave up for all values of x greater than 0. The fun part is this graph right here looks like it is never going to be concave downward. There is no interval in this sign chart where our second derivative was negative. And because the second derivative is never negative, there's never a change in concavity right here. So we would say that this graph has no point of inflection. Again, there's never a spot here where the concavity changes from up to down or vice versa. So this graph is a little bit different, or this function I should say is a little bit different than some of the other ones we've been working with. But I think when we put all that together, guys, that answers those first 2 questions. And then on the previous slide, I think we had answers to the last 2. So yeah, that's number 45 all put together there, guys.